Welcome to the AI seminar. We're going to have Dustin Morrill give his final PhD seminar. Dustin has been a longtime member of the Computer Poker Research Group going back to when he was an undergrad and did his master's and now his PhD. Was one of the members of DeepStack, the team that produced the first program to beat professional players at No Limit Texas Hold'em. And has done a whole variety of work inside of game theory and learning algorithms within that space that we'll hear about some of that today. So take it away, Dustin.
Yeah, thanks very much, Mike. I'm really excited to be here today giving my thesis seminar. Thank you so much for coming. And today I'm going to talk about foundations of hindsight rational learning for sequential decision making. Need to get the slides to go. All right, there we go. So just to give you a quick overview of my thesis, the topic is on scalable reinforcement learning algorithms for environments that are complex, non-stationary, and could be filled with many learning agents. My thesis question is, in sequential decision-making settings and with minimal assumptions, how can we define rationality in a learning context? And how can computationally restricted learning agents utilize their own experience to strive toward this notion of rationality? So I'm going to be talking about things related to that in this talk. The general approach that I've taken in my thesis is to repurpose regret and traditionally studied ideas about regret for deviations to past behavior as hindsight rationality, a learning objective that incorporates an agent's concrete experience of the environment, applies regardless of the number of other agents in the environment, and the other agents could actually change, or the number of other agents in the environment could change dynamically, and has strong connections to game theoretic equilibrium concepts. It also readily motivates algorithms that can be practical to implement, computationally efficient, and empirically successful. So for today's talk, I'm going to narrow in on just a smaller subset of my research. And I'm going to talk about hindsight rationality, which I mentioned on the previous slide, as a general learning objective. I'll talk about how hindsight rationality mixes with sequential decision-making, as I mentioned in my thesis question as well. And then I'm going to talk about a specific type of deviation, and all these terms will get more clear as we go on with concrete examples. But I'll talk about the counterfactual deviations, which is a special small deviation set that are useful for designing algorithms. Then I'll talk about observable sequential rationality and the sequential decision-making deviation landscape. And then I'll talk about an algorithm that uses all these conceptual foundations called extensive form regret minimization that achieves observable sequential hindsight rationality for a broad and natural class of deviations. I've given talks around these topics before, but this talk is going to emphasize different aspects. So I hope if you've seen some of my talks before, that things will be new. In particular, I'm going to be focusing on the topics around some corrections that have been made to two of my recent papers, thanks to a counterexample that Revan McQueen showed me like a month ago or so, and these corrections are maybe the best possible kind of corrections because they didn't impact our concrete theoretical results or the algorithmic results, and they also led us to get a deeper understanding of the topic and the ideas that I'm going to present today. So that's the plan. And I will get started now. Oh, actually, before I get started, if anyone has any questions or comments, please interrupt, raise your hand, or just start talking. And there'll be a place where I will ask for feedback as well. So don't be afraid to unmute and start talking. All right, with that, I'll get started. So first, I'm going to talk about hindsight rationality. That's going to form the basis of the rest of the talk. So often in AI and reinforcement learning, we will the workflow that we'll tend to use is we'll take some environment, some task, we'll do a bunch of computation on it, and then we'll use that computation to produce a policy or a plan to deploy in the real world, perhaps. And ideally, that policy is intelligent in some way. Now, this makes a lot of sense in stationary environments where we can do training procedures that come up with optimal policies, at least in principle. And so these policies really do achieve the maximum payoff that you could hope to get within these environments. And so once we do this training procedure, we can do it once, and then we can deploy it whenever we need to solve our problem. So this can be really useful. However, as soon as we move to the setting where we have a second player, things get a little more complicated. In zero-sum settings, which is the simplest version of this, there's no longer a universal optimal policy, but we can still take this approach and it can be effective in practice. But instead of finding an optimal policy, we're going to try to find an optimally robust policy. And that typically has the form of a Nash equilibrium. So it turns out that when you find a Nash equilibrium in a two-player zero-sum game, that you can take any of the strategies, deploy them against any other strategy, and you'll achieve, you'll maximize your minimum payoff, regardless of what the other player does. So this is how we solve poker games, and Deep Stack as well is based on this idea. But once we move to the multiplayer setting, more than two players, or if we have general sum payoffs, so we could have some opportunities for cooperation between the agents, then there's both no universal optimal policy and Nash equilibrium is less useful. So it's one thing, it can be difficult to actually compute a Nash equilibrium, but even if we did, or if we approximated it, you still probably wouldn't want to deploy a strategy generated from a Nash equilibrium because it can perform arbitrarily poorly depending on what the other players in the real world actually do, even if those players are themselves playing part of a Nash equilibrium. If it's not the Nash equilibrium that you used or that your strategy is part of. So Nash equilibria in this setting are not interchangeable, so you have this equilibrium selection problem. What my thesis has been pushing towards is to avoid this whole training deployment dichotomy where we generate these static artifacts and instead focus entirely on the learning procedure. So we're going to have objectives for dynamic agents that are learning as they're solving your problem, whatever that problem is. So hindsight rationality then starts from this picture where an agent is choosing strategies over time and learning as they go. We can imagine that their experience is discretized into rounds. So an agent produces a strategy pi t on round t. Other agents produce their strategies sigma t at the same time. And then these strategies are evaluated in the environment. Afterwards, the agent receives a payoff function v given the strategies that the other players used, sigma t. And then that agent can use this payoff function to improve their strategy for the next round. So what this looks like rolled out over t rounds is that the agent will have produced t different strategies. And this is the concrete realization of the learning algorithm. And then we can assign, and then we can look at how much reward the agent has accumulated over that time. And so that's the average of the payoffs that they've accumulated given the other players' strategies. Now, one thing we need to make this make a little bit more sense is we need a baseline to compare the agent to, because it's not enough to say that the agent got an average reward of 5. We don't know exactly what that means. So we need some comparison point. And we can do that with a deviation function phi. So this is going to generate alternative behavior. We apply this function that maps strategies to other strategies. We can apply it to each of the strategies generated by the agent, and that's going to generate a whole new sequence of behavior that has its own average payoff. And then we can compare the learner's payoff to the average reward accumulated by any deviation in a set capital phi. The hindsight rationality goal is then for the agent to accumulate at least as much reward as the best deviation in their set, with some leeway that's going to 0 as the number of rounds increases to account for the fact that the agent doesn't have foresight. So this is the hindsight rationality objective. Another way this is often formulated is that we'll take these two sums, we'll take the difference of them, and we'll call that regret. And then this objective is equivalent to minimizing regret. Yes, Alex. Go ahead. I see you have a question.
Alex's magic. This is the deviation from the agent's policy. It's not a kind of global with respect to the environment thing.
Yes, it is a deviation to the agent's behavior, exactly. And it's in fact a function of the deviations or the agent's behavior in general. You could imagine the simplest actually deviation function, and we'll see examples of this, but the simplest deviation function is one that just maps to a static strategy, right? So we could replace the agent's behavior with some fixed strategy. And then effectively the agent would be comparing to the best fixed strategy in hindsight, right? This is a common thing that people do.
Thanks.
Yep, thank you. Okay, so we have this hindsight rationality objective. We can connect it to regret minimization, which has been studied for decades. The important thing about hindsight rationality here is the framing, that we're not minimizing regret in order to solve some optimization problem. Instead, we're using it as motivation for an agent to accumulate and maximize their reward. So this is really a reward maximization objective. And this leads to an important subtlety of this objective as well. So notice that, it's a backward-looking metric, because these sums can only be evaluated after the agent has played in the world for T rounds. But if the agent is actually hindsight rational, it has a guarantee, a future-looking guarantee, that it will achieve this before you even deploy a hindsight rational algorithm. You know that for every round in the future, this guarantee will be achieved, which means that you can actually improve the performance of your agent by adding better and better deviations to your set capital phi. So in effect, from this forward view of hindsight rationality, you can interpret the deviations as telling the agent how to actually maximize their reward, at least in part. There are a lot of details, and we'll talk more about those going forward, but that is the kind of intuition I think is useful. Okay, so now with that, now that we've established the hindsight rationality framework, we can make some connections with traditional notions of rationality. So it happens that if the deviation set capital phi contains the constant deviation functions, the ones I mentioned before, these are also called the external deviations. They just map every strategy to one deterministic pure strategy. Then it so happens that a hindsight rational agent in a stationary environment will achieve nearly optimal performance. So effectively, hindsight rationality subsumes the optimality objective that we started talking about early in the talk. As well, in a 2-player zero-sum environment, if both players are hindsight rational for this deviation set, then you achieve convergence toward a maxi-min, minimax, Nash equilibrium. So again, this notion of rationality, in effect, subsumes the type of rationality that's useful in these 2-player zero-sum games. And then regardless of what the deviation set contains, in any environment, if all the players are hindsight rational, then you achieve convergence towards what's called a correlated equilibrium, and it's parameterized by the deviation set. But this is basically a generalization of the Nash equilibrium idea to distributions over joint strategies between all the players. So then the algorithm design pipeline looks something like this. We'll take an algorithm and deploy it as a learning agent in the world. That agent will choose strategies and improve their behavior over time, interacting with the other agents. One other quick thing I forgot to mention about this picture is that the other agent, at least for our purposes, isn't going to reason explicitly about the other agents. It really is only going to learn from the feedback it receives from its payoff function. Go ahead, Rich.
Dustin, none of your words or equations have probabilities or expectations in them. So can you explain that?
Yes. Okay. So all of this is assuming, at least for my thesis, everything is all of these values. This payoff function is an expectation. Now this makes the theoretical results simpler to state and I think easier to reason about. But I don't want to take that as a limitation of this approach. There are definitely, and in fact, extensions have already been made to the case where you don't receive expected payoffs from these values and where you evaluate your strategies completely. You can think about the bandit online learning setting, for example, and there you only get stochastic feedback, but it fits into this picture as well. Nothing really changes in this picture. It really just adds extra aspects of complexity that are really interesting and necessary for scaling. But I'm leaving that for future work. But it definitely, all these things, essentially these payoff functions just need to evaluate the strategy, and we can approximate that with Monte Carlo, right, samples of the payoffs. Go ahead, Rich.
I'm sorry, but it's in particular, you said that you would be, once you had seen the behavior, you would know absolutely the values, and that would not seem to be possible in any generalization.
I agree. Yeah, in general, you don't know exactly how well your policy is going to do. In fact, like evaluating counterfactuals is a hard problem that people have been struggling with forever. Right, you can't live the same day twice, and all of these things. And this algorithmic or this framework is definitely assuming that you can receive that counterfactual information. But I think this is still useful because of the estimations that we can do in order to get that information, at least in part. And as I mentioned before, like the bandit setting, studying that, there are ways that you can get useful information by like periodically sampling. Effectively exploring the space allows you to estimate the counterfactuals that you need in order to do this kind of reasoning.
Thank you, Dustin.
Yeah, thank you. Go ahead, Amy.
Oh, well, if Rich is happy, then maybe I don't have to add anything. I mean, I just thought that it might be worth mentioning that we have randomness kind of in two parts. Like we have it on the part of our agents, and then we also have it on the part of the environment. And I wasn't sure which one Rich was asking about, but you might have been resolving one or the other in different ways. Like, for example, worst case over the environment, right? Not taking expectations, but taking expectations over the agent's behavior. So I thought maybe something like that could help clarify.
Thanks. So yes, the randomness here is, there could be randomness in the world, like die rolls or shuffled decks of cards. You could be playing poker, right? So there's definitely randomness there that you would want to average over. Then there's also randomness in the actual policies. Usually you can deal with this in the same kind of way with Monte Carlo sampling kind of approaches, and that leads to a lot of interesting, difficult questions for sure. But conceptually, I'm not going to deal with that right now. Go ahead, question. Kirby. Yeah.
Hopefully a very quick one.
Sure.
The leeway there is order 1. Is that constant with respect to time or the number of other agents? Both, neither?
Yeah, subconstant in the number of rounds. So it should be going to 0 over time, as the agent learns. Yeah, thank you. All right. Yeah, with that, I'm going to move on. Thanks very much for all these questions. I'm really happy to get engagement, because a lot of times when I give this talk, there's not a lot of engagement, and I wonder if I'm just losing people. So this has been great. Thank you. All right. So connecting with traditional notions of rationality, I talked about correlated equilibrium. Right. So the Hindsight rationality pipeline looks like this. So we're going to do play and learning. And then from that play, if we wanted to, we could record the strategies that all the players use, and we could evaluate them. We could evaluate the agent's regret, and we could also check if the joint strategies are converging toward a correlated equilibrium. And then given that we could perform this evaluation, that's going to inform the way that we design our algorithms in the first place. And so it makes sense then to design our algorithms to minimize regret for a given deviation set. And the algorithmic problem becomes, how do you design efficient algorithms for stronger and stronger deviation sets? So we're going to talk more about that going forward. All right, now I want to talk about, so far everything has been kind of in the one-shot setting. I want to talk now about sequential decision-making and where that fits in. So for sequential decision-making, I think about game trees like this, where player 1 is going to choose left or right, and then player 2 acts, and then player 1, and then maybe there's a chance outcome, like the roll of a die or drawing a card from a shuffled deck. And then eventually the game ends at one of these terminal histories labeled Z1 to Z3. To account for hidden information, like cards that I don't get to see, or actions that are happening simultaneous to the ones that I'm taking, we can incorporate what are called information sets. This is just groupings of the histories where different players act, or where the same player acts rather, denoting the fact that they don't get to observe the history exactly when they're acting. So for example, here I have the player 2 acting nodes grouped together in an information set, so they don't get to see whether player 1 chose left or right before they act. Effectively, player 1 and player 2 here are acting simultaneously. So this is kind of a traditional view of games with sequential decision-making, and the formalism is called extensive form games. But for designing the kinds of algorithms that I'm interested in, it's often more useful to think about the subjective view of this game from each player's perspective. And so if you take the information sets and you encode them as states, you reach the formalism that I designed called partially observable history processes. And these pop trees look something like this. On the left, you can see that player 1 takes an action, and then there's an outcome that happens due to external forces. And then player 1 acts again, and then the game ends after that. And for player 2, the game looks like they act once, and then there's some extra outcome, and then the game ends. So the strategies in a pop, they look like this. Here's an example pop, and I'm going to show what a strategy looks like in this domain. Formally, it's just an assignment of actions to each state. To be clear, it's a pure or deterministic strategy. We can also have mixed or stochastic strategies. And here's what the always left strategy looks like. So in every state, we take the left action, and the agent ends up at the LLL outcome and receives the payoff there. So now there's a question: how can we integrate sequential decision-making into our learning model that we had with Hindsight rationality? So one answer to this question is that on each round, so each round could represent a step in a single continual pop. So then the agent's actions will be really simple. These AT, this AT denoted here, and then after they take that action, they receive an observation. Now, this is a really interesting setting, but it's going to be a little bit too complicated to tackle right now. This is actually something that I want to, I've been talking with Mike and Amy about for a while and want to work on it more in the future. But instead, we're going to focus on a different model, which is that every round in our Hindsight rationality picture is going to represent the evaluation of an entire pop. So we're going to have a repeated pop that we're going to work with. So now the important thing to notice here is that strategies are these complicated plans about how to behave in the pop. And the payoffs are also complicated functions that depend on how you act in every state. Right, so this is what deviations look like then in this repeated pop setting. So you take, for example, the always left strategy and you transform it into a strategy here that's playing left, left, right, right. One problem that arises in this setup is the exponential blow up in the number of strategies, because like I said, they're very complicated objects. So we have 5 agent states that we can see in this pop with 2 actions each, which means there are 2 to the 5 or 32 different strategies. So even if we want our agents to compare against every fixed strategy, this is going to get very difficult as the game grows. And this becomes even more of a problem when you want to consider more complicated deviation sets, because there are at least 32 ways to transform any one of these given strategies, and therefore 32 to the 32 possible deviation functions. So if we wanted to track values for each one, we would be out of luck for any game that is of any reasonable size. So controlling that complexity while trying to achieve the strategic strength that these deviation functions give us is going to be the theme for the rest of the talk. So now I'm going to talk about one particular subset of deviation functions that are actually efficient to deal with. And even though they're restricted in some important ways, we can recover a lot of the strength that we're losing in the restrictions with by making use of the particular structure of sequential decision-making environments. So a counterfactual deviation plays to reach some particular part of the state space and otherwise leaves the strategy unmodified. So for example, here, this deviation is modifying the strategy at the first 3 states. And then afterward, the 2 remaining states, it just leaves the strategy unmodified. This is really nice because these counterfactual deviations are defined by a state and an action. Therefore, there's only 5 times 2 equals 10 of these counterfactual deviations in this visible part of the pop. So it grows linearly with the state space, much better than exponential. These deviations are called counterfactual because they're because of a connection that we'll make to a prominent algorithm called counterfactual regret minimization, and we'll talk about that later. And they're called blind because they don't look at the strategy before they choose before they compute the output deviation strategy. So it is the changes that it makes to the strategy are consistent regardless of what the input strategy is. So then we can draw a picture that represents the whole set of these blind counterfactual deviations because they all have a similar form. They all modify the strategy with these red edges along some path until they reach some target state, and then they leave the strategy unmodified everywhere else. And so that's the red zigzag here represents the changes that are being made, and the black triangle represents the fact that we're leaving the input strategy unmodified for the rest of the game. Now, as pointed out by Revan McQueen, this restriction, this deviation set, actually has some important limitations. And so I'm going to go into that example now. And like I mentioned before, this has been added to the one of the papers that I published in AAAI last year as a correction on arXiv. So you can take a look at that for more information. So here's the counterexample. We have two strategies, and so the agent here, you can imagine that the agent, generated these two strategies across 2 rounds, and they achieve an expected value of 1 because they take the left action and they get a value of 1. If they were to take the right action, then there would be an outcome determined by chance or another player that would lead to 2 identical states. But in those states, the agent happened to choose the worst outcome, the left action that always gives them -2. So if we consider a counterfactual deviation here, we could start playing the right action. We would have to do so under both strategies because it's just a fixed transformation. And then we would only be allowed to change the action in one of the 2 successor states where the agent is acting, which means that in under one of the strategies, we will get +2. And under the other strategy, right, where the other player is controlling the outcome, we would get -2. So we would get an expected value of 0. And so there's no beneficial counterfactual deviation here. And like I said before, we can kind of interpret this as saying that the counterfactual deviations don't tell the agent where they can get more value. They're not expressive enough to do that. But there is a beneficial external deviation, right? If we just change all of our actions to the right action, then the agent will get a value of 2 under both strategies and an expected value of 2. So in our papers, we said that the counterfactual deviations subsumed the external deviations, but that's not quite true because of this example. Now, there is actually a way to recover the strategic strength of the external deviations, but it requires an extra property, one which we talked about in the original paper, but we didn't connect it to this example. And that is observable sequential rationality. So the idea of observable sequential rationality is that it's not enough necessarily to perform well just from the start of the game. Maybe you actually want to perform well in every subtree of that pop. So this is saying here, so we have 3 states, and the agent goes right in the first state, but it's considering a deviation to go to the left, which would take it down to this successor state on the right. These 2 states are what we call observable, and under observable sequential rationality, play there has from both of those states, right? Assuming you get there, it must achieve the hindsight rationality condition, right? It's not just enough for the right action to be strong. You have to play well at the successor agent state that you could end up in if you were to take a deviation. At this other node, at this other state, this state is unobservable because the other factors in the environment don't let you go there. And so then play can be arbitrary. So we're actually relaxing the traditional conditions of sequential rationality that have been discussed in game theory. And so that's why we qualify this as observable sequential rationality. So now going back to McQueen's counterexample, we can see that if we can see that the initial strategies were not observably sequentially rational for the counterfactual deviations, because we would need to play the action at the successor agent states would have to be different, would have to be stronger in order to be observably sequentially rational. So this is a minimal change here. So under the first strategy, you would have to play the right action in the successor state. And then under the second strategy, you would have to play the right action under the other successor state, the right successor state. And so once you have this, so it turns out that achieving observable sequential rationality with respect to the counterfactual deviations is enough to give you this payoff. It will give you this behavior where you play well at each of the sub-states, which means you're safe to choose the right action in the root and get the extra value. We can formalize this with a theorem that says that if the agent's full regret at each agent state where they're acting, given the sequence of strategy profiles, with respect to every blind counterfactual deviation, if we have a bound on that regret, depending on basically the depth of the game, but yeah, technically the number of external action transformations in counterfactual deviation phi, then the agent's observable sequential rationality gap with respect to the blind counterfactual and external deviations is actually no more than this FT, this bound that we had originally for the counterfactual deviations, multiplied by the number of agent states. So the number of states could, of course, be large, but relative to the number of rounds that you're going to run could be quite small. Yes, Amy, go ahead.
Just a quick question, not so much about the theorem, but can I understand this as like a way to characterize external deviations as kind of counterfactual deviations plus this observable sequential rationality property?
Good question. The answer is no. There are examples where, in fact, even without observable sequential rationality, the counterfactual deviations can outperform the external deviations. So it isn't, in fact, that the external deviations always do better than the counterfactual deviations. There is like a mismatch. Neither one subsumes the other. Until you add observable sequential rationality, then they become equivalent. That's not quite true, actually. Observable sequential rationality improves the strength of counterfactual deviations, and they could still be stronger. They will just subsume the external deviations. Yeah, thank you for that question.
Thanks.
Okay, so this says that if we achieve observable sequential rationality, we can work with the counterfactual deviations, but still achieve the strength, and in fact surpass the strength of the external deviations. All right, so now we can start filling in a space, a deviation landscape for these sequential decision-making problems. At the opposite ends of the strength spectrum, we have the external deviations at the bottom that I've mentioned before, that we've been talking about already. At the top, we have the internal deviations. So this is like the full mapping, essentially, or has the same strength as that of deviations. So you can have deviation functions that map one strategy to any other strategy. And then in between, now we can put the blind counterfactual deviations that are weaker than the internal deviations, but they subsume the external deviations as long as you have observable sequential rationality, and that's denoted by this dashed line. I'm also noting here that each of these deviation types corresponds to a correlated equilibrium concept that's been studied in game theory. So the external deviations correspond to coarse correlated equilibrium, internal with correlated equilibrium, and counterfactual with counterfactual coarse correlated equilibrium. And you can see the references where these concepts are described. And in fact, we can start filling this out more with other deviations that people have studied before. So one on the left here are the blind causal deviations. And these were studied by Farina et al. And they correspond to the extensive form coarse correlated equilibrium concept. Another deviation type are the action deviations. These are really simple. They just change the action of one at one state, but exactly one state. And these are associated with agent form coarse correlated equilibrium. And so I defined these equilibrium, this deviation type and equilibrium type in the AAAI paper as well. One interesting thing to note is that these causal deviations look kind of like a flipped version of the counterfactual deviations, because the causal deviations go to some part of the state space and then they modify the strategy afterward. So that's an interesting difference. Notice that there are actually no lines connecting these different deviations, right? So we don't have a line, for example, saying that the causal deviations are stronger than the counterfactual. Because we actually have examples in the AAAI paper that show that these are, that none of them subsume any of the others, even with sequential rationality. Furthermore, there are some other deviations that people have looked at that are really just variations of the ones we've seen before. And these are the informed versions of the deviations we've looked at. So all they do is they look at the action at a single state, and they choose their next action and strategy accordingly to that. So they condition on a little bit more information than the blind deviations, but otherwise their structure is the same. And these correspond to extensive form correlated equilibrium, counterfactual correlated equilibrium, and agent form correlated equilibrium. The first and the last one were described by von Stengel and Forge earlier. So now, so now I want to make another addition to this picture, because as I mentioned, there aren't any arrows connecting the different concepts in the middle of this picture with each other. So why can't we have a deviation type that, for example, subsumes all of these deviation types? And we can get an idea from the relationship that we have between the counterfactual and the external deviations. And notice how the blind causal deviations look really similar to the external deviations, except they have this extra black zigzag that represents not modifying the strategy at the start of the game. So maybe quickly, can anyone tell me how we might draw a deviation set that's a superset of the counterfactual and action deviations, but it will also subsume the causal deviations with observable sequential rationality? Does anyone know what that would look like? All right, I guess I maybe lost too many people. I'll have to just, in the interest of time, I guess I'll have to just give the answer. So the answer is that we can draw it with a black zigzag and then a red zigzag and then a black triangle. So this first part, right, looks like the counterfactual deviations, and that's going to deal with this like external part. And then we have this black zigzag that deals with this part of the blind causal deviations. And we call this deviation type the blind partial sequence deviations. And the nice thing about this is that just like the counterfactual deviations, we can easily count the number of blind partial sequence deviations because it's only deviating along a single path. And it's, so the number of these grows, it grows linearly with the number of states and a factor that depends on the depth of the game. And in fact, we can get a generalization of the previous theorem where showing that the strength of this type of deviation gets elevated with observable sequential rationality. It turns out that the counterfactual and the blind partial sequence deviations can be defined as what I call a single target deviation. It's a transformation, it's the transformation shown here that we take the original deviation set capital phi, and we construct a new deviation phi prime that only applies that deviation in states that are predecessors of some target state S, but otherwise leaves the strategy unmodified. And so once you make that construction, usually this set of single target deviations will be smaller than the original set. But you can show that your observable sequential rationality gap, if you achieve observable sequential rationality with respect to this single target deviation set, the observable sequential rationality gap with respect to that set, as well as the original capital phi, is bounded by this same amount that on average is going to go to 0 over time across rounds. All right, so I know I'm almost out of time, so I'm going to quickly run through the rest of the slides. Yeah, I'll quickly go through this. We can fill this deviation landscape out even more. We can add deviation types that subsume the informed versions of these deviations, and then have one deviation type that subsumes all of those. And then we can go even further and come up with a deviation type that corresponds to something von Stengel described when he was talking about informed causal deviations and extensive form correlated equilibrium. This deviation set is called the behavioral deviations. It's impractical to actually be hindsight rational with respect to the behavioral deviations, because the number of them grow exponentially with the depth of the game. So not just the states. So it's better than the internal deviations, but it's still exponential in the depth. So it's going to be hard in general. But we're going to have an algorithm called extensive form regret minimization that, given any set of behavioral deviations, will achieve observable sequential hindsight rationality with respect to the single target version of those deviations. So it ensures that it's actually efficient, relative to the size of the deviation set. So quickly, how does this algorithm work? Well, it looks at local learning. So it asks, how much would an action transformation at this state S improve the agent's return under their given their current policy pi t? To know this, we need to know what the return is for every action if pi t is played afterward, and that's just the counterfactual value. Think about this as just the expected return, slightly generalized. And then we need to know how often does the agent following a deviation reach this state, which depends on the deviation. And here's where things get a little tricky. So if you're considering many deviations, you can have many different probabilities of reaching this state. And so you have to deal with all of these at once. So we're just going to keep track of all of these reach probabilities for all the deviations. this gives us a whole set of regrets, a regret with respect to these counterfactual value functions, all weighted by different reach probabilities. And it turns out that controlling a set of weighted regrets is actually, it's been studied before. And so Blum and Mansour present this problem and a kind of a basic algorithm for this. And it's the setting is called time selection, because over time, these reach probabilities, across rounds are changing. And so you need to keep track of all these different weighted regrets. But once you do that, you can minimize simultaneously the cumulative weighted regret across all weightings. And we provide a new algorithm for this that has some nice features called time selection and regret matching. I'm not going to go into that, but that's the name if you're looking up the paper later on. And then if you run this algorithm at every state, so do this local learning at every state, you can show that the algorithm EFR, given a deviation set, capital Phi, is observably sequentially hindsight rational for the union of Phi and the single target deviations generated from Phi. And the computation and storage demands also scale with the complexity of the single target deviations. So that's very nice in terms of computational efficiency. And the way that this proof works is by regret decomposition. So if you minimize the regret at these child states here, if you minimize regret there and you simultaneously minimize regret at the parent S, then it happens that the two-step regret, so if you consider deviations of length 2, you also minimize regret for those. And that's where we get our efficiency win. And then if we instantiate EFR with different deviation types, we get different previously studied algorithms. If you use the blind counterfactual deviations, you get counterfactual regret minimization, which has been successful in playing poker games, for example. If you take the informed causal deviations, you get an algorithm that's like internal CFR, which was described in an award-winning NeurIPS paper in 2020 by Chelly et al. And then if you apply the blind counterfactual deviations, you get an algorithm that's basically policy gradient policy iteration. In fact, you can think about this black zigzag as, well, actually the black zigzag and this black triangle as telling you to do on policy learning, if you're familiar with that from reinforcement learning, because you're only making these local changes and all of them are dependent on the actual policy that you're sampling from. Then we can get new variants of EFR. So we get if you use the twice informed partial sequence deviations, you get an algorithm with complexity that's based on the depth and the number of actions cubed. If you use the causal partial sequence deviations, it's the complexity is the square of the number of actions. Same for CFPS. And the blind partial sequence deviation scales with the depth and the number of actions linearly. Some quick highlights of the empirical evaluations we did with EFR. So thanks to EFR's generality, we can test the hypothesis that just changing the deviation set, having an algorithm that competes with stronger deviation types, does that lead to better performance? And in fact, in some small benchmark games from OpenSpiel, we do actually see that generally stronger deviation types do induce better play. And you can see a bunch of these results in the ICML paper listed here and its supplementary material on arXiv. Now to conclusions, hindsight rationality is a reinforcement learning objective that embraces environment complexity. Hindsight rationality, though, can be difficult to achieve in sequential decision-making settings because there are too many strategies and deviations. So we need to have clever ways of designing efficient algorithms. But efficiency can be recovered by curating the set of deviations and then using observable sequential rationality to boost their strength. And EFR efficiently achieves observable sequential hindsight rationality relative to its given deviation set. And in addition, EFR inherits a lot of the, essentially all of the numerous developments that have made CFR scalable and effective in real settings like two-player no-limit Texas Hold'em, for example. And it's a single agent reinforcement learning algorithm because it never actually explicitly reasons about the other agents, and yet it has multi-agent guarantees. And I think this paradigm is really exciting for the future of reinforcement learning research. And as well, the experiments show the deviation set does in fact have empirical practical performance implications. And that's my talk. Thanks very much for listening. I'm happy to take questions. Thanks.
Thanks, Dustin.
Feedback. Thank you.
Audience. Feel free to just jump in. Yeah, you can. Go ahead.
So what's the kind of key entry points into this? Is it thinking about a set of deviations, or is it more complicated than that?
Yeah, I mean, I think so. I mean, I guess the way we,
Sorry.
I guess
You're good to go.
way, thanks. I guess the way we started with this is we had algorithm, CFR, and we wanted to understand that better. And that led us to investigate these different deviations. And then, the loop kind of came back to say, well, now we can construct these new deviations, and how do we modify CFR in order to actually use them? But I think, now that we have this kind of theoretical conceptual basis, I think it's reasonable to look at deviations that are interesting first, and then design an algorithm to use them afterward. I mean, of course, it definitely helps if you have an algorithm that you just want to modify. But I think that's where, as well, the connections to past algorithms is really useful. Like I said, we connect to CFR and internal CFR, and I'm trying to make connections to reinforcement learning algorithms. And so I think there's a lot of interplay between the design of these deviations and the design of the algorithms that use them.
Okay, because I think the idea of hindsight rationality is possibly really relevant to those of us kind of concerned with the continual learning paradigm and how it functions. But then I don't know CFR that well, so that's not the easy entry point for me.
Sure. Okay. So yeah, the question or the comment was about continual learning and how would one get started about using. It seems like this could be really useful for continual learning, but it's hard to see where to get started. And I agree. That actually goes back to one of the earlier slides, right, where I talked about the fact that you could imagine that every round of this process is actually just a step in a single continual pop, like this. The problem is this doesn't fit neatly into the story I gave before, around equilibrium, and it doesn't work so well when you think about applying a deviation through the entire pop, modifying a strategy everywhere. The way we define deviation functions, right, is mapping from strategy to strategy. And it's not clear exactly what you would be competing against in this setting. But I'm actually actively working on this, and there are some ideas that are related to other ideas of regret, like policy regret, for example. And this is where the regret metric kind of changes underneath you. And I think it's better understood if you think about it in terms of this sequential decision making. single, continual learning pop. But there are definitely difficulties in, writing that out properly and designing an algorithm for that.
Gotcha, thanks.
Yeah, thank you.
All right, we're past 1 o'clock. So if you have more questions, please follow up with Dustin, and let's thank Dustin again.
Thank you.
Bye, everyone. Have a great afternoon.